have a talk about some dynamics of solutions of chemotaxis-growth systems. Okay, not hearing yet. Okay, yeah. So, okay, this title is changed from my original title. Okay, so my original title is some about modified Fitz-Nagumo systems. So, but the topic of this conference is some chemotaxis and cross-diffusion. So I changed my mind last week, and I changed the title to this. So, okay, so the new title was is not reflected in abstract notebook, but in the corner of abstract, this correct title is written. And I also I was also asked Professor Mimura to have a talk related to this topic. So I changed my mind. Okay. Last week. Okay. So anyway, today I would like to talking about some existence of periodic solutions appearing in chemotaxis growth systems. Okay. So this is a joint work of Izuhara and Mimura. Okay. First, let me brief explain which kind of periodic solutions consider here. Okay, so called generally relaxation oscillations. So this is a very simple examples of ODEs possessing relaxation oscillations. So in this case, this equation include some small parameter like this. So as the first dynamics, putting epsilon equals 0 like this, we get this equation as the first dynamics equations. So then the dynamics according to this equation is like this. And then and after approaching enough to these branches, we can consider the slow dynamics. So in this case, we change time scales like this and transform this equation by this new time scale. In this case, the slow time scale is from capital T. So then this equation becomes like this. So then, then the first equation is some algebraic equation. So by solving this equation and substituting it into here, so then we can get the some dynamics along these branches. So as a result, we can get some periodic solutions like this. So first change, first dynamics and slow dynamics and fast dynamics and slow dynamics. In that sense, we call this kind of periodic solutions possessing fast and slow dynamics or alternatively relaxation oscillation here. So so this is some very simple examples for ordinary differential equations, but there are a similar kind of periodic solutions in partial differential equations. This is some example which was shown many years ago. So this is some conversion model equations. So in this equation, theta corresponds to the temperature in some sense, and N corresponds to some concentration of fuels. So and the fuel, so the boundary condition of temperature is 0 degree boundary condition like this, and fuel is supplied through the boundaries like this. So in this case, but this fuel is very effective fuel. So that is by small fuel, by small fuels we get very high temperature like this. That is epsilon is sufficiently small in this case. So then, okay, if we put formally epsilon equals 0, then okay, fuel is almost constant like this, lambda, and substituting lambda into this equation, we get some approximate equations with respect to theta. So then, okay, so and this is a picture of the global bifurcation diagram with respect to lambda. Okay, so for this equation, so the horizontal line corresponding to lambda. So then, if lambda is sufficiently small, then only low temperature stationary solution appear. But if lambda is sufficiently large, then only okay high temperature stationary solution appear. And in the middle range, so there is some structures like this. So that is some hysteresis structures like this. Okay, so this is the case. Lambda is constant, but epsilon is sufficiently small but not 0. So this lambda changes very slowly like this. So with small time scale like this. Then after reaching these branches, solutions moved slowly along these lines like this. And here the branch disappears, so the solution go up. Okay, this one. go up like this, and okay. So like this, okay. Slow dynamics and fast dynamics, slow dynamics and fast dynamics. Also. Like this, okay, some relaxation, oscillation, periodic structures appear also in this conversion model equations. Okay, so this is a very old result. So in this talk, okay, a similar kind of in this talk, we would like to show the existence of similar kind of periodic solutions in a chemotaxis-growth system. But the structure is not quite same to this equation, to this periodic solution, slightly different structures. Maybe such structures is some kind of new. So okay, I would like to show later. So okay, anyway, okay, this is our main topic from here. Okay, so in today's talk, okay, I would like to deal with some chemotaxis-growth systems. Okay, so some the model equation is describing some aggregation phenomena of cockroach-like aggregations, like this. So okay, so in order to obtain our model equations, okay, let me briefly explain the background, okay. So okay, some amoeba, okay, like E. coli, gathering by a chemotactic attractant. But if we just look at each individual, then it is known that there are no directional movement. So each individual moves randomly. Okay, so maybe a similar discussions was already mentioned in yesterday's talk by Professor Kim. So okay, so quite similarly to this case, okay, in macroscopic level, okay, we can observe some aggregation phenomena by chemotaxis, but each individual move randomly. Okay, no directional movement. So then, okay, even if okay, each individual move randomly, okay, can we observe aggregation phenomena macroscopically? It's the question. So, this is some motivation I already mentioned. So, thank you. So, by the existence of a chemoattractant, what is different? So, if there are no chemoattractant, each individuals, of course, moved randomly, but the movement is rather fast. So, but if each individual feel the existence of chemoattractant, then their movement slow down a little bit. That is So by assuming such phenomena, we just impose the following conditions. That is, there exists some critical concentration of chemoattractant, and if the concentration of chemoattractant is lower than that the critical value V star, then the movement of individual is rather fast, like this. And if the concentration of chemoattractant is beyond such critical value, then they prefer to stay. Of course, it moves randomly, but the velocity of movement becomes slow. So that is prefer to stay. So that is we assume the some switching phenomena like this. With some critical concentration of chemoattractant. This is a simulation. If total numbers of individuals are small, then even if we assume such conditions for the movement, we cannot observe some aggregation patterns like this. So if the number is rather low, then no aggregation pattern. So this is initial data, but it diverges randomly like this, no patterns. So but if we put more individuals, then some clustering patterns can be observed like this. But of course, each individual move randomly. Only the velocity of movement changed depending on the concentration of chemoattractant. So then, even if each individual move randomly, so we can observe some clustering patterns like this. If the number of cell becomes larger. So this is the case. So we put so many number of cells. Then, there are many clustering. Rather than it, there are several empty regions like this. So anyway, so our consequence is like this. So even if each individual move randomly, if the velocity of movement changes depending on the concentration of chemoattractant, then some clustering patterns can be observed like this. So then, okay, so by these simulations, okay, now we construct some mathematical model, okay, describing like this. Okay, so now here, okay, N is the density of individuals, so like equally. So and we divide this N into two phases, N1, N2. And N1, okay, of course N1 and N2 are randomly walking, but the walking rate is by a different ratio, D1 and D2. Okay, so we assume D1 is smaller than D2. Okay, it means N1, the phase N1 is okay, phase N1 corresponds to less active phase, and N2 corresponds to active phase. Okay, randomly rather fast. Okay, so and we normalize the ratio of switching condition. Okay, here. Like this. Okay, so that is H and K is the sum switching ratio from one phase to another phase. I just normalize like this. So then, okay, we get this kind of mathematical models. Okay, so okay, here, okay, U1, okay, is the population density of a less active state. Okay, and U2 corresponds to the active state. So active state means, okay, so diffusion ratio is rather large compared with this. So in this case, so plus some constant, positive constant alpha, like this. And they change to from one phase to another phase by this. And V is the pheromone concentrations. Of course, pheromone is produced from each cell. So that is so a plus terms like this. Okay, and by using these three-component systems, okay, we consider the dynamics of these solutions. So, but this okay, so looking these equations, okay, we just use the difference of random movement, but this equation is really reduced to some chemotaxis or cross-diffusion systems formally, at least formally, like this. Okay, I just explain here. Okay, so now we assume epsilon is sufficiently small. So it means the switching occur very rapidly compared with diffusions. So then, okay, so okay, since epsilon is sufficiently small, so formally we assume this relation holds. Okay, so then, okay, from this relation and other is this relation. So K plus H equal 1. Then by using this relation, U2 is represented by this. So substituting this into here, okay, then and U is the total concentration, that is U1 plus U2. So then this equation is reduced to only the equation of U by using this relation. So and by adding each term of U1 and U2, then we get this equation and substitute this into here. So this equation equivalent to this. So this equation is some equation and of cross-diffusion type equation, and we calculate this Laplacian term. Then this equation becomes like this. That is, so this term is something like corresponding to a diffusion effect, and this part is correspond to the directed movement depending on the gradient of kV. Okay, like this. Okay, this three-component system can be reduced to some cross-diffusion type equations, at least formally. So, but later some rigorous proof for the relation of this equation and this reduced equation. So the rigorous proof was given by Funaki, Mimura, Urabe, and Izuhara, 2020, and also okay. So Professor Murakawa showed the relation of cross-diffusion system and other type of reaction diffusion systems by using similar considerations. Of course, Professor Murakawa got this result faster than them. Okay, like this. Okay, so these three-component systems can describe the chemotactic aggregation phenomena. Okay. So, okay, we by using these three-component systems, we consider the following. Okay, so okay, for simplicity, we consider this equation on one dimension. Okay, so then okay, it is easily known that this quantity is preserved in time. So we denote mu of this quantity, and this system has specially constant equilibria. Okay, say phi 0 mu. Okay, of course, such a stationary, constant stationary state, constant stationary states are parameterized by this preserved quantity. So of course it is parameterized by mu, and anyway, so this constant stationary state is given by this explicitly, like this, by using this mu parameter mu. So and I check the global bifurcation structures with structures of stationary solutions with respect to this preserved quantity. Then, okay, so this is a numerical picture. But okay, so this line corresponds to the constant stationary solution. Okay, phi 0 mu, and it is stable here and here. But around here, okay, some bifurcation occurs, and there appears some new branches like this. The spatial profile of each branch is like this. So this is a spatial profile of U. Okay, U is the total concentration U1 plus U2, and this line corresponds to the profile of V. Okay, chemoattractant. So, and this branch is just a reflected solution of this. So, like this, okay, from constant solution, some spatially inhomogeneous stationary solution bifurcate like this. So, and this is global bifurcation structures for these equations. So, but in this equation, some total density is preserved. So, but if we add some gross terms to this equation like this, okay, Fisher KP type gross terms, and of course, okay, we assume delta is sufficiently small, then okay, what happens? So it's the problem here. So okay, of course, okay, okay, we already observe if delta equals 0, then some aggregation patterns can be observed. So, but what happens if some growth term is added, like this. So, this is a very complicated bifurcation structure. Okay, so this is a numerical pictures of bifurcation diagram with respect to delta. Okay, so here if delta is rather large, then only constant state stable. But delta becomes a little bit smaller, then some patterns appear like this. And here, and along these lines, so the pattern changes like this. And around here, so this region corresponds to the delta is sufficiently small. Then around here, some periodic behavior appears. That is, if delta is 0.9, then some periodic appear. And changing delta smaller and smaller, then the frequency becomes larger and larger. That is, a period of oscillative solution is longer and longer if delta becomes gradually small. So it is observed by this numerical picture. Okay, so this is a summary of a bifurcation diagram with respect to delta. Okay, so here only constant solution exists and stable, and here a non-constant stationary solution appear, and in this region, delta is sufficiently small. Then periodic behavior appears here. So and in this region, period is longer and longer as delta becomes smaller and smaller. So then how does solution behave when delta is sufficiently small? Okay, so this is a time profile of this solution. Then this behavior just like relaxation oscillations. So what kind of mechanism is induced in this system? So as mentioned before, so now so we assume delta is sufficiently small. So that is the growth term is sufficiently small. Then we can divide the dynamics of this solution fast and slow dynamics. So actually, so the taking integration of this, so this part just disappear and only this part remains. So if we define mu is the total mass of U1 plus U2, then the equation of total mass formally are given by this, by taking integration of these systems. So then, similarly to the relaxation oscillation case, first we can consider the first dynamics of this equation. That is, putting formally delta equals 0. Then this equation like this. So as mentioned before, this quantity is preserved in time t in this system. So then the first dynamics becomes like this. So this is a global bifurcation structure by numerics. And this horizontal line, so not m, just mu. So if total density is around here, then for example, if we look at around here, then there exists a three stationary state like this, and a constant solution is unstable. So then it becomes like this or like this. So anyway, so this is a flow with respect to these equations. So as mentioned before, this branch corresponds to this inhomogeneous patterns, and this branch is the reflected solutions of this. So like this, solutions approaches to each stable state like this. So okay, then okay, next we consider slow dynamics. Okay, changing time variables like this, and putting delta equals 0 formally. Then we get this kind of equations. So then okay, this part means okay, the solutions are sufficiently close to these branches. So then okay, we have to consider the dynamics along each lines. So then okay, the equation for mu is given by this. Okay, so denoting f mu. So then okay, at least okay, along the constant stationary branches, then okay, it is easily check okay, the solution approaches to this region like this. Then okay, what is the sign of Fu along these lines? So this is also a numerical simulations. So okay, that is around here. So it's positive, and it's negative and negative. So it means okay, so this is a summary of the dynamics. Okay, so okay, first okay, so by first dynamics it approaches to the stable stationary state like this, and along this line okay, it moves to this directions, but the branch disappear here, so it have to go down to the constant stationary solution like this, and along this constant stationary solution it moves like this, and this behavior is repeated. So we can expect the existence of relaxation oscillation dynamics here. So okay, this is a numerical simulations. If delta equals 0.1, then it behaves like this, and if we take delta equals 0.01, then okay, the period becomes longer like this. The time profile is like this. So okay, okay, yeah, okay. So I omit this part. So of course okay, we can similarly okay consider the 2D case, but 2D case is very complicated and no time. Okay, so I just skip the 2D case. So okay, okay, then okay, now okay, we can expect the existence of a relaxation like behaviors for this system. But how about the mathematical proof of this equation? Okay, so this is a mathematical models which we consider here, and added some small gross terms like this. So we just write these equations in this vector valued forms. Okay, so okay, as mentioned before, okay, so already the another type, okay, already we know the existence of relaxation oscillations in some PD models. In that case, the structure of relaxation oscillation is like this. So this is a very usual type of relaxation oscillations. But in our case, the structure is slightly different. That is, in our case, okay, so this part is the same. But still, okay, unstable constant solution remains here. Okay, so okay, usually, okay, so please remember the general type of relaxation oscillation has a structure. Okay, like this. Okay, no solutions around here. So, but in our case, still some unstable constant solution exists here. So then, okay, how solutions can go to branch? Okay, so this is a very difficult point in our case. So okay, so now okay, almost no time. Okay, okay, I just mentioned about the result only. Okay, so now okay, okay, so we denote some linearized operator with respect to this constant solution, okay, L0, and we assume several things. Okay, I just briefly mentioned our assumptions. Okay, so of course the spectrum of the linearized operator with respect to constant solution, the distribution of spectrum is like this of the linearized operator with respect to constant solutions. Okay, so and we also the some magnitude of this intervals. Okay, so now the branches of constant solution and non-constant solutions is like this. The parameter corresponds to mu minus mu c. Okay, so we say mu minus mu c. Then okay, we can expect the existence of some periodic solution between these regions. Okay, so then okay, at least between these regions, this interval satisfy these conditions. That is okay. Here okay, some another spectrum approach to zero, but the movement, the region of movement of this spectrum is restricted in some regions, limited by gamma zero. But the other spectrum is apart from more than 2 times gamma zero. Okay, so but this is a very technical condition. But anyway, so we assume this kind of assumptions, and okay, and we have to do several assumptions, and also assumptions. So this assumption is very a little complicated, but by using pictures, it is very clear. Okay, so now this is bifurcation structures with respect to mu, and this is a bifurcation branching. So now, okay, these assumptions is the existence of the connecting orbit. So that is, we assume the existence of connecting orbit from here to here, and from okay, that is from constant solution to non-constant solution. Similarly, the existence of connecting orbit also around here. So okay, so if we can check or we can assume the existence of such connecting orbit, then okay, we can prove the following. Okay, so this is okay our final result. Okay, so now okay, we would like to construct the periodic solutions like this. So, but still this unstable constant solution exists. So we have to carefully check the dynamics along these constant solutions. Then, by using Center-Manuel theory, we can get the very, very precise dynamics along these constant solutions. Then, by using these informations, okay, everything given explicitly like this. So, this is our final result. Okay. So, okay, okay. Of course, okay. Around here, solution moves like this, and here no branches, so the solution go down like this. And along this constant solution, it becomes larger and larger. And first, okay, we just expected the solution go up here, but in this case, it's not. That is, the solution does not go up here, but it goes slightly moving along this constant line. Then another mu star, it goes up like this. So okay, so please remember the structure of original relaxation oscillation phenomena is like this. Okay, but in this case, okay, this branch still remains. So slightly different structure appear like this. Okay, it doesn't go up here, but slightly move along this line and go up. And this mu star is just given by the constant by this quantity. Okay. So this is a numerical simulation. Okay, numerical simulation very suggesting this theoretical result is correct. Okay, so this is concluding remark, and already time is over, so thank you for your attention.